there, right? So the remaining matrix, that is what you call the Mij there. Okay, this minor entry. So for example, this one, then you will pick the AI, this row, not to solve for your Aij there. So we have there Aij, and then after that, we multiply the remaining of the matrix here, right? And we get the determinant of that. And this is now your Mij. We remove the ith column and then the jth column. This is now an n minus 1 by n minus 1 matrix. So next we have another definition. A is a square matrix, then the number Cij. Now for the Cij, we will add the sign now, the sign of your Mij. It's if it's positive or negative. So negative 1 to the power of I plus j there. This is the power. For example, you have there 1, 1, A11. If you pick A11, this becomes 1 plus 1 here. And 1 plus 1 is 2. So negative 1 squared is positive. That is why it's positive in A11. Okay? Then multiply your Mij there, which is this matrix. Right? If you delete the first column and then the first row. So it's called a cofactor of entry Aij. So next we have this one. This is solving the determinant with the cofactor expansion of A. This one. So to see this, by the way, class for the determinant, it's okay to pick a row or a column. It's here. Is it okay? It's okay to pick a row or a column. So it's up to you. So for example, this one, if you pick the first row, so that's A1j times the C1j is there. And then the C1j's are equal to this, negative 1 to the power of 1 plus j times M1 of j. So we will now apply it. So for example, if n is equal to 1, the entry is only A11, so the determinant is equivalent to the number A11 there. Next, if your matrix is a 2 by 2 matrix, as you remember, when we saw the determinant here, it's A11 times A22 minus A21 times A12, right? So this one. Now applying the Mij's, we have this one. First, we pick the first row here. So A11, we have there negative 1 to the power of 1 plus 1, and then M11. Your M11 class is the result when you remove the first row and the first column. So that's A22 will remain. That is why M11 here becomes A22. Next, you have A12. If you pick A12 there after, that becomes negative 1 there to the power of 1 plus 2, because that is the placement, right? 1, 2 there. So 1 plus 2. This becomes negative, correct? This is 3 here. So this is a negative 1 to the power of 3 is a negative number. And then what is your M12 there? So remove the first row and the second column. The remaining number here is A21, which is here. You multiply A21. This is your M12. Okay, next. When n is equal to 3, okay. This is the formula, again, summation. Pick first row. You have your A11, so it should be M11 also, the same number. A12, M12, A13 here times M13 also. And look at the negative 1 exponents. So first, 1 plus 1, second, 1 plus 2, then last is 1 plus 3. So for the A11, if you pick A11 there, so remove the first row and first column, then you have this 4 numbers remaining, and this is your M11. Okay, and the same process goes to M12 and your M13 there, and that's it. This is now the formula for your 3 by 3 matrix. Okay, using the summation. Next, you have this one. Find the determinant of A if your A is this matrix. So here we pick the first row. We have there 1 times the C11, 2 times C12, and then 3 times C13. Now we separate it like this, the computation. We separate the C11. But if you want to use this number 3 formula, it's fine. The results are still the same. So here using the cofactors, we have there C1, 1. So we have the negative 1 to the power of 1 plus 1. Then remove the first column and first row. You have there remaining number 2, 1, 1, 5, which is this. Then get the determinant of this one. So the result is positive because this is 1 plus 1 here. So negative 1 squared is positive 1. Multiply 2 times 5 and then minus 1 minus times 1. And we got 10 minus 1 is equal to 9. Now C12 is expected to be negative because this is 1 plus 2 here, and that is negative 17. And here for C13, then you will be confused like, oh, why is this negative now? By the way, class, here it's positive here, but the determinant here that you can solve is negative because 4 times 1 here is 4, then 3 times 2 is 6. So that is 4 minus 6, it becomes negative 2. Okay, then substitute it here in your uh, formula for the determinant of A. You have there 1 times C1 plus 2 times C12 and then 3 times C13. And you have these values. And then the answer is negative 31. Okay, next. Smart choice of row or column. So here, class, we can find determinant using cofactor expansion along any row. So along any row that you want. But our first examples are just about the first column, first row. So here we can pick also by columns. So it's up to you. So it's here. It will be easiest to use cofactor expansion along the row or column which has the most zeros. Yes, because you're going to multiply the zeros there to the other cofactor and it will be easier to solve. So we have this in example class, and this is very easy to do if you pick the R2 here, row 2, correct? Because row 2 contains 2 zeros there and only one number 2. So we have here 0 times your C21. The location here is row 2, column 1. That's why it's C21 here. 2 times C22, row 2, column 2 location, and then 0, C23. So the 2 here are zeros, so we can only compute this 2 times C22, and it's easier to do. So 2 times negative 1, and then the power is 2 plus 2 because this is 2 here. And then remove this row 2 and column 2. The remaining numbers are 1, 3, 3, 5, so which are here. Then 1 times 5, it's 5. Then 3 minus 3, this is 9. So 2 times 5 minus 9, it's negative 8. Okay? And that's it. Very easy to do, right? Only one, you only solve one of them. And then next, how about this? Um, this column 3 here has 2 zeros, so it's easy to do if you solve this part here, only this. So we have there 3 times the C13, and the 2 are 0 already. So 3, and then to the power, negative 1 to the power of 1 plus 3, again, because this is C13 here. The exponent is 1 plus 3 also. Now remove the third column and the first row. You have here 2, 1, 3, 1. Remaining numbers, 2 times 1 minus 3 times 1 there, or 1 times 3. And the answer is negative 3. Okay? So very fast to solve if you pick those rows or columns with most zeros. So next we have here how an elementary row or column operation on the square matrix affects the value of its determinant. So if we switch a row or if we switch columns, what will happen there is the determinant of the B, your matrix here, B is equal to the negative determinant of A. Now, if we multiply a lambda in your row, in one of the rows or in one of the columns, then the determinant of B is equal to lambda times the determinant of A. And then if you perform this one, the determinant of A and B are the same here for all lambda element in K. Okay, next. Corollary 2.1, a square matrix with two equal rows or two equal columns, then the determinant of A is equal to 0. So if you notice something like this, that there are two equal rows and two equal columns, Two equal rows means the rows there have the same entries, for example, and that's it. The determinant of that is 0. Okay, that's it, the explanation. Next, if the square matrix with two proportional rows or two proportional columns, then also determinant of A is equal to 0. This is the reason there. Um, Next, you have used row reduction to evaluate the determinant of this. So what are we going to do now is to make all these numbers are not zeros, right? So we're going to do something like making the other numbers their zeros so that it's easier to solve the determinant. Okay, so for example, this one. First we apply this one r2 minus r1. Then you can get your new r2. So this 3 here becomes 1. Correct? Yeah, because you minus this, negative 5 minus 3 is negative 8. Then we have here 2 minus negative 4, it becomes 6. So next now, what we're going to do, since this is now 1 now, it's easier for us to make 2 and 5 here be zeros. Okay? And that's it. There are now zeros if you perform this row operations. And now, as you can see, it's easier to solve now the determinant because in this column, it's only, we solve only this part here, right? So we have here 1. This is row 2, column 1. So the power of negative 1 is 2 plus 1, correct? So we have here 1 and the negative 1 to the power 2 plus 1. And what to do next, remove the second row and the first column. You have here 19, negative 16, 44, and negative 27 are the remaining numbers. Now get the determinant of this. So 19 times negative 27 minus, you multiply 44 minus 16, so that becomes plus there now. And the result is this, negative 191. It's negative because this one is a negative number here outside because it's 3, it becomes 3 here, right? A negative 1 cube is equal to a negative number. And that's it. Next, we have this determinant of a matrix product. And for this part, there is, what do you call this? Part in the exam that solving something like determinant of the products there. So you have to um, memorize these formulas. So we have here, if the A and B are square matrices of the same size, then determinant of the product AB is equal to the product of their determinants. If the determinant of A times determinant of B. So if you have this one plus A and B, and this is your AB, you verify this. The determinant of A there is negative 6. Determinant of B here is negative 246. And the determinant of AB is equal to 1476. Okay? So you try to solve the determinant of this if they are equal. Next, you have this one. Um, by the way, class, I am sure that they are equal. You just have to try this to solve them individually. Okay, next you have this one. If A, B are square matrices of the same size, the determinant of A plus to the power of a number k there is equal to the determinant of A to the power of k. So it's look like the exponent, you can write it outside the determinant of A. Because the reason is this one, determinant of A to the power of k means determinant of A times A, where A k times is equal to applying our rule for the product is we have the determinant of A times B is equal to determinant of A times determinant of B. So this one, since all of them are A's here, and that's it, we can make it determinant of A times determinant of A times determinant of A, and this is K times. Therefore, that is determinant of A to the power of K. Next, what if there's a number there? I saw something like this in the test. If there's an alpha there, and this is a number, so times AB there, matrix AB. What will happen to the alpha class? It has an exponent n there. then multiply determinant of A times determinant of B. And then you will ask me, oh, what is that n there? Okay, the n here, class, is the size of your square matrix. So if your determinant, if your A there and B are 3 by 3 matrix, so your n here becomes 3. Okay, and this is the explanation. If your matrix there is 2 by 2, your n becomes 2 here. Okay, so you have an example. So evaluate the determinant of x if x satisfies this equation. So first get the determinant here, then determinant of x equals the determinant of this matrix. Now this is easier to do. Here you can pick this number here, uh, choosing column 1, or you can choose row 3 because only one entry is here also. So if we pick this one, the A11, so it's 1 times negative 1 to the power of 1 plus 1, and then get the um, remove this, and you get the determinant here. This is 1 times 1, 1 minus 0 times 4, it's 0. So 1 minus 0 becomes 1 times 1 there, it's 1. So the answer here is 1. So 1 times determinant of x, then the answer here in the other side, it's 3. So 1 times determinant of x, that's determinant of x, which is equal to 3. Now, if the answer here, class, is 2, for example, or yeah, if this is 2 here, you have to divide the 2 to the other side. It becomes 3 over 2. Okay? Because the number here, it's only 1. So 1 times determinant of x, it becomes determinant of x. Okay? And that's it. Next. If you have something like this, then evaluate a to the power of 2011. So what to do first, get the determinant here first, determinant of your a. And it's easier to do if you pick row 1, because only one entry. And if you solve that, it's actually negative 1. Okay, you check that. And we have here determinant of a to the 2011. You can write the 2011 outside. Now, since the determinant of a there is negative 1, raise that to the power of 2011. It's equal to negative 1. So, class, for the negative 1 numbers, class, if the exponent is even, the answer is positive 1. And if the exponent there is odd number, the answer is a negative 1. Okay, next. You have this one. We have determinant of 2ab. This is your a, this is your b there. So again, the formula is you raise the 2 there cube because these two matrices are 3 by 3 matrix. And you have the determinant of a times determinant of b. 2 cube is 8. Now determinant of a here is 3. Then the determinant of b is 2. Please check that. For A, it's easier to pick 3 there, right? The row column 1. Here also column 1 is okay to pick. And the answer there is 2 for B. For 3, the determinant is A. Multiplying the three numbers now, 8 times 3 times 2, the answer is 48. So please compute their determinants and check if this is correct. Next, you have there, let A be an m by n matrix. So the minor of A of order k is the determinant of a k by k submatrix of A. So for example, this one, find the minors of order 3 of the matrix. So first, you can remove the fourth column, the third column, the second column, and the first column. So you have here 4 answers. But I will just give you the first only one. So we remove the fourth column there, and you have this. So it's here. We obtain the determinants of order 3 by keeping all the rows and deleting one column from A. So just deleting one column. So there are 4 different minors of
What's going on,
order 3
everybody?
here because we have here 4 columns, correct? But we will compute only one of them, and this is it. Remove the fourth column, and you have this. It's easier to get the determinant here, right? So 1, you pick column 1 here. So 1, and then after that, negative 1 to the power of 1 plus 1, so it's positive 1. Then remove the first row and the first column, then remaining this numbers here. 2 times 2, it's 4, minus 2 times 4 here is 8. So 4 minus 8, it's negative 4. So this is the determinant, negative 4. And next. So the minors of order 3 are called the maximal minors of A since there are no 4 by 4 submatrices of A. Next, let A be an m by n matrix. The rank of A is maximal order of a non-zero minor of A. So example class, if this one, we go back, if all the minors of order 3 here becomes 0, if the determinants are all 0, for example, then this order 3 is not a maximal minor of A, minors of A. Now you pick a 2 by 2 matrices here after, okay? If that will happen, so that you can get the rank, because the rank of A there is the maximal order of the non-zero minor of A. So we have an example here. Find the rank of the matrix A, and we solved this already. And the answer is negative 4 if we remove the column 4, right? So this is not 0. Hence, the rank of A is 3 because uh, maximal minor now is order 3. Here, another example. Um, Rank of this matrix A. Now, if we remove the column 4, you have this one, and then the answer is 0. By the way, if you get also, if you remove also column 3, column 2, or column 1 there, all the determinants are zeros. So it's here. The other 3 are all 0. Now, since all minors of orders 3 are all 0, the rank of A is now less than 3. Now we pick 2 by 2 matrix there from here. We have here 1, 2, 9, 5. We pick that matrix and get the determinant. 1 times 5, it's here. Then minus 2 times 9, we have negative 13 is the result. And this is not 0 anymore. Now, if this is not 0, therefore the rank of A now is equal to 2. Because the 2 order now is the maximal. Okay? It is now the maximal minors of order 2. And that's it. Your rank of A now is equal to 2. Next, you have the sum properties of the inverse. If the square matrix A is invertible, if and only if the determinant is not 0. Oh, so it means, class, that if you solve the determinant, if it's not 0, then you can find the A inverse there in your matrix. And another property, the determinant of A inverse is equal to 1 over determinant of A. And it's actually equal to the determinant of A raised to the power of negative 1. Okay? And that's it. Here, this is the reason. Next, if A and B are invertible, then AB is also invertible. AB inverse is equal to B inverse A inverse, and then you will ask, oh, why this switch this? Okay, class, this is correct, and you cannot switch this to A inverse B inverse. You will get a wrong answer. So this one, class, is the inverse of AB because when you multiply this with the matrix AB, the result is identity. So this one, then you apply associative property. A inverse now times A is equal to I now. Then this becomes B inverse times B now. And this is also equal to identity I. That is why, this is the reason why the A B inverse is equal to this, B inverse A inverse. And the alpha A inverse is equal to this, 1 over alpha A inverse. Okay, that's the reason. And then A inverse inverse is A transpose. If you get the inverse of that, it's the A inverse transpose. And if you have here as a unique solution, equation AX is equal to B, your A class is multiplied here in the left side of X. So you multiply A inverse in the left side also. And left side also here in the other side of the equation. So you have your A inverse here. Now, if you multiply A inverse in the right side here of the B, and that is not the correct answer anymore. Okay? Here, multiply it in the left. So multiply here also in the left of B. And that's it. Next, you have here XA equals B here. This is now the equation. If you solve the X there, since your A is located at the right side of X, your A inverse will be multiplied here in the right side. So that A times A inverse becomes identity I, and that becomes X. Okay, so your b here will be multiplied a inverse in the right side also. And if you have here the last part, you have there a x b equals c. So your a is here at the left side, so multiply that a inverse. So a inverse is also multiplied in the c at the left side. Your b is here in the right side, so multiply that with b inverse. So it becomes x is equal to a inverse c b inverse. And if you have this one, okay, now your matrix is in the left side. You multiply the inverse here at the left side also of the other side of the equation. So you have this one. Okay, this one inverse times this. Now, if you switch the inverse here to the other side, because it will give you a different answer. Okay, and if you multiply them now, the answer is this. So first, get the inverse of this one first before you multiply. Okay, next. How about this? This matrix is in the right side. So you multiply here the inverse in the right side also. So that's it. And this is the answer. Okay, next. Lastly, okay, if they have here two matrices. So here the left side, so multiply the left side here with the inverse, and then this one multiply the inverse in the right side, and you have this one. Now get the inverses first, then substitute it here, then before you multiply the three matrices, and you will get this value. And that's it. And it's 9:51. It's time now for your break time. By the way, class, the LMS is it? Not yet responding. Ah, it's okay now. Okay. So I will upload now the materials there. So you can access it now, class, the slides there, determinants, system of linear equations, and then applications of system of linear equations. Okay, so it's time already. Next, we have linear equations, system of linear equations. We have here definition, non-homogeneous linear equations, and then homogeneous system of linear equations. So she is Cynthia Cooper of the WNBA Houston Comets basketball team. Was named Team Sportswoman of the Year by the Women's Sports Foundation. So Cooper scored 680 points in the 1988 season. And then in the basketball tournament, you have here 1.2 points and then 3 points. So the total score is 680. So if you make that as an equation for let x be the 1 point, and then 2 is y, and then 3 point you have there is z. So you have there x plus 2y plus 3z is equal to 680. This is the equation that you can have it. Next, you have um, by hitting 413 over 1.3 point and then 1 2 point and then 3 point attempts. So here is the total points that he got. So we have there 413 shots. So we have here x plus y plus z is equal to 413. That's the total of the shots that she has. And then the last is she made 40% of her 163-point field goal attempts. So it means this one, z over 160 is equal to 40% or 0.4. Um, so question is, how many 1, 2, and 3 point baskets did Miss Cooper compete? So we're going to solve the x, y, and then the z there. Okay? Oh, where's the next? Okay, and that's it. First, it's easy to do the z first here. Just multiply 160 there in your zero point 0.4 and you will get 64. And substitute it here in the values. Okay, and your calculator can solve that already. Just transfer the numbers there. You have there x plus 2y now is equal to 680 minus 3 times your z is 64. So minus 3 times 64 there. And then this one you have there x plus y is equal to 413 minus 64 because this is z here. Transfer here minus 64. And your calculators can solve that already. Your x is 213 and then your y there is 139. And that's it. We solved them already. Next, we have system of linear equations. In two unknowns arise connection with the intersection of lines. So if you have two equations in two unknowns, that we have two unknowns here, x and y, and your calculators can easily solve it actually. Okay, so there are three possibilities. First, lines may be parallel, so no intersection, so no solution also. If the lines may intersect at only 1 point, then the system has exactly one solution. And then if the lines may coincide, it has infinitely many points of intersection, so infinitely many solutions. So you have here two parallel lines, so no solution. Here, one solution only, the 1 point here in the intersection. And then here, infinitely many solutions because they coincide in just one line. Actually, they're just the same lines. And for the three unknowns, you have this one. If the intersection is something like this, then it's only 1 point here. You have unique solution. Next, if the planes intersect something like this, then your intersection here is one line. So it's infinitely many solutions because you cannot count all the points here in one line. Next, if you have something like this case, like here, only two of the matrices intersect here, on also here, and there's also this line here. So there is no common intersection between the three. Okay, here also two matrices intersect with two what do you call this? Two planes intersect with this one, and there is no common intersection between the three, therefore no solution also. And here they are parallel. Okay, your the graph of your equation is parallel lines. So the general system, linear system of m equations is that in the n unknowns can be written as like this. Okay, where your A, I, J there are the coefficients of the system. Then BI are constants from I1 to M, then J from 1 to N, and then your X sub 1 there up to X sub N are the unknowns. Okay, and we have this information. Next, definition 1.2. A solution of the system 1 is a sequence of n numbers S1 to Sn such that the equations in the system 1 are satisfied, then we can substitute the values there in your x1 up to xn. Okay, next, definition 1.3. Matrix A with entries Aij is called the coefficient matrix of the system 1. Okay, if you will just get the coefficients there and you have this one. This is your coefficient matrix of the system 1. We just get the AIJs there and that's it. Next, if we add this other column here with the BIs, so this is now what you call an augmented matrix for the system 1, which obtained by adjoining the column B to matrix A as the last column here, the last column. So this is your X matrix containing X1 to Xn, and your B is B1 to Bm here. Okay, if you multiply this with your matrix there, AMN, so we have your AMN times X, which is an n by 1 matrix. The result is a Bm by 1 matrix. And this is your B matrix here. So the system 1 is called homogeneous if your B is equal to 0. So if the column here if the entries here in your B are all zeros, then that is homogeneous. And non-homogeneous if B is not all zero or not equal to the zero matrix M by 1. So for example, class, your matrix is 1, 0, 0 here. So B1 is 1. That is not considered now class as a zero matrix, so it's non-homogeneous. Okay? Even if one entry in your B matrix is not zero, so it's non-homogeneous already. So every non-homogeneous linear system has this one, no solution or unique solution or infinitely many solutions for your non-homogeneous. A linear system is consistent if it has at least one solution, the unique one, or the infinitely many solutions, and inconsistent if it has no solutions. Okay, so we have this information. Next, example 2.1, solve the linear system. This one. Um, your calculator can do this directly, and you can have there 4 over 3 for your y, and then x is equal to 7 over 3. But if you solve this, we add the negative 2 times the first equation and add that to the second equation to eliminate the x because this is x here and this is 2. So if you add the negative 2x here, it becomes 0. So negative 2x added here 0. This one, negative y multiplied by negative 2, it becomes positive 2 plus y. It's 3y. And the answer is 4 here. That's it. If you multiply negative 2 here plus the 6, it's positive 4. Now divide 3 both sides. Your y is 4 over 3. Then substitute it here in the first equation. If your y, you can solve the x there, which is 7 over 3. So that's very easy, class. If only x and y here, only two variables in two equations. So how about if too many? So it's easier if you have there the augmented matrix AB. Okay? Then if you solve that, what we're going to do is here, just reduce it to row echelon form. So using your MATLAB, it's very easy to do. Just type the matrix there, and then if you label it with C, then C is equal to, then you write it there, the RREF of C, then you're done. So operations that lead to equivalent system linear equations, we are done with this already, right? Interchanging two equations, and this one multiplying lambda, and then this one. So we obtain new system that has same solution set but easier to solve. So for example, this one. What is our goal here is to make this reduced row echelon form, or the row echelon form only. It's fine. For this one, just get the numbers there and form this augmented matrix. And applying this, R2 is your R2 minus 2R1, and then your new R3 is from R3 minus 3R1. So that this becomes 0 here, the 2 becomes 0, and the 3 becomes 0 also. And this will happen after that one. Now, after this, for the second row, to make this one here, because we're going to make this one, right? um, you can multiply the second row by negative one third, correct? Yeah, you can do that, and then um, the whole rows there you can multiply it with negative one third. But what he did there is different one. He added the negative of the row three, so it's there. R2 minus R3 there, and this will be the result for your R2. It becomes now 1, 4, 6. Now make this negative 4 0. Okay, so we add 4 in the R2. I multiply 4 in the R2, then add it in your new R3 to get the new R3. And we have the 1, 0, 0, 0 here now. Then the remaining numbers here in the third row is 8 and 10. So, by the way, the slide stops there already. But you can make this one if you wanted to. You can multiply here 1 8. 1 8 in your row 3. Okay. So what happened is they make this already. Substitute their x1 in the first column, x2 in the second, and x3 here. Then add this and equal to this values here, 7, 6, 10. Now solving your x3 there, it becomes 5 over 4 because you divide it by 8. And 10 divided by 8 is 5 over 4. Substitute the value in x3 here in your second equation, and you can solve it. 5 over 4 here. So 4 times 5 over 4 is 5. Transfer to the other side. So 6 minus 5, it's 1. And then here you substitute now your value of the x sub 2 and x sub 3 in the equation 1, and you can get the x sub 1, which is 5 over 4 also. And this is the unique solution. 5 over 4, 1, comma, and then 5 over 4. Next, if you have this another example, and then you form the augmented matrix. Then after that, make this 0 and 0 here. So this will happen. Next, this is 1 already. So make the negative 1 here 0. Just add the R2 and R3 there, right? Yeah, it's here R3, R2 to get the new R3. Now what happened, class, is all the numbers in the rank 3 become, in the row 3 becomes all zeros. So if that happened, by the way, I give you a hint there. Actually, we discussed this already in the vectors side. So what will happen here is that you are going to um, give the x sub 3 here, the value is equivalent to a variable t there, such that your t is element in the set of real numbers. Okay, that is what we did there previously. And we have these two equations only remaining. So again, your x3 there, we can substitute any value or any value. Yeah. So that's it. Transfer there. So we have the x1 and x2. Just transfer the other parts there to the other side. Okay. Now next, what will happen is your x3, they have it arbitrary value. They use alpha here, so it's okay. And later we will use another t there. By the way, if you say like, can we use letter t there? Yes, it's okay. Alpha is just a arbitrary variable that we can use. So since if we let x sub 3 be equal to alpha, substitute it here in the alpha in the equation. So negative 2 plus 10 alpha, it's here, negative 2 plus 10 alpha. Now you substitute this in your x2 here to get the x1, and then your x2 here is alpha. Then solve this one. The answer is 5 minus 17 alpha. You have their three values already now. So the solution is this one. The system has infinitely many solutions. 5 minus 15 alpha, then negative 2 plus 10 alpha, and then your x sub 3 is alpha. So again, class, please remember, if your row 3 becomes all 0, that will happen. Your x sub 3 there, it becomes an arbitrary value. Okay, you can use any value there. Now, what will happen if not all zeros in the third row? There's a number there, the last, the B in the B column. So that is this example. So solve this equation, system of linear equation, by Gaussian elimination again. So make the augmented matrix here. And after that, make this two threes here be zero. So that is why we have this. Next, we make this one here. So to make this one here, it's nice here if you multiply this by 1 over 9. Yeah, and that's it. R2 divided by 9, or 1 over 9 times R2, we have that one. Then make this 0 here. So apply this, negative 6 times your row 2 plus your R3 to have your new R3. And now, class, this happens. As you can see, they're all zeros here, but there's an 8 here. So if this will happen, class, this is now, the system has no solution because of the last part. They're all zeros there, and it's equal to 8. This is false. 0 will never be equal to 8. So that is why this system has no solution. Okay, so if it has no solution, class, no value for x3, x2, and x1. Okay, so this is the only case that if the system of linear equations has no solution, if all zeros here and then there's a number here. Next, a system of linear equations is said to be homogeneous if the constant terms are all zero. So we have here 0, 0, right? This is, yeah, and that's it. So this is now homogeneous equations. So the trivial solution is x is equal to 0, 0, 0, which is correct, right? If your values of x sub 1 there up to x sub n are all zeros, then this will be true. The equation will be true, correct? Now, non-trivial solution if your x are not all zeros there. So homogeneous linear system always has this one, only the trivial solution, or infinitely many solutions in addition to the trivial solution, that is non-trivial solutions. So homogeneous linear system 2 has non-trivial solutions if and only if your rank of A is less than n. Your n there is the number of unknowns. Again, it has non-trivial solution if the rank of A is less than n. Now, if the rank of A is equal to n, then the system has only trivial solution x is equal to 0. And this one, um, additional, if R of A is less than n, it says there it has non-trivial solution, and additionally, it has infinitely many solutions also. Okay? Here, rank of A is equal to R less than n, plus the R here are different from each other. The R here is the rank function. The R here is a number. Okay, it's not the same R here. Okay, so the system 2 has general solution. You have this one. So T1 here, if you have there T1 and here Tn minus R. So these values here are arbitrary numbers which are called free variables. And I will give you an example where we can have the free variables. Again, if your R there, if the rank there is less than our n. So for example, this one, and you solve this, just write the constants here, the coefficients. Do not include the 0, 0 column anymore because when you do the elementary row operations, they are not affected. There will always be zeros there. Okay? So first, this is 1 here. So make this 3 rows here be 0. This one, The 1, 2, and 1 here. Make them all 0, then apply this elementary operations, and you have that. Next, you make the negative 1 here be 0, and the 2 here becomes 0, so you have to apply this elementary operations, and you will obtain this. Now, you can make this 0 by adding this one, the R4 and R3, and you have this now. Okay. Plus, as you can see, the negative 2 here, you can make it 1 by multiplying negative 1 half here, correct? But they didn't do that anymore. It's okay. Now, what is the rank of your matrix now, class? The rank is 3, correct? Because this is 1, 1. Actually, you can make this 1 also, right? By multiplying again negative 1 half here in the row 3. So yeah, the only 3 is the rank. It's not equal to 4. So it means that if the rank is less than n there, you have free variables, right? So your free variables here now, class, is the this one, the variable in the third column and the fifth column, because they do not have the leading ones. Okay, and the free variables are x3 and x5. Okay, that's how to determine the free variables. So what does it mean to be a free variable? It means that you can substitute there an arbitrary value. So we substitute, like example, x3, we let that to be t sub 1, and then x5 to be t sub 2 later. Okay, so this one, we rewrite it like this now. We substitute the x1, x2, x3, x4, x5 there. And then after that, we solve the three values. We have your x1, you can solve it like this. Your x2 is this, and your x4 is 0, correct? You start here in the lower part, divide negative 2 both sides. Your x4 is still 0. Then substitute it here, x4 is 0. Then your x2 is negative 2x3 and negative 3x to the x5. Now what to do, substitute this in your x2 here. Your x3 remain, your x4 is 0, then your x5 is this. Then transfer all them to the other side, and you can form this for your x1, 3x3 plus 5x5. And you have these values. So next, what we're going to do, we let x3 be t1 and then x5 be t2. So since there are free variables, your x3 is t1 here, your x5 is t2, your x4 is 0, because x4 here is 0, right? Now you substitute here with t1 and t2 in your x3. X3 is t1, your x5 is t2, and you will get these values here. Your x1 is this, 3t1 plus 5t2, and your x2 is negative 2t1 minus 3t2, where t1 and t2 are arbitrary numbers. Now, if you want an specific solution for this one, you can put a value for your t1 there. If your t1 is 1 and your t2 is 2, then you can substitute it here and solve it. Okay? And that's it. Next, we have the application of linear equations. First, we have network analysis, electrical circuits, and then balancing chemical equations. So a network is a set of branches through which something flows. Okay, so example, this one, 1.1. The branches might be electrical wires through which the electricity flows, or pipes through which water or oil flows, or traffic lanes through which vehicular traffic flows. So in most networks, the branches met at points called nodes or junctions where the flow divides. So if there if generally some numerical measure of the rate at which the medium flows through a branch, for example, this one, okay, then flow conservation at each node, the rate of flow into any node is equal to the rate of flow out of that node. So you remember this again, the rate of flow into any node is equal to the rate of flow out of that node. So example, we have there 1.1, find the flow rates and directions of flow in the branches. Okay, so you have this direction. For here, 30, it goes in, out here, and then goes in here in 60, and then it goes out here, flow out. Okay, if we label them, A, B, C, D there in your nodes. Okay. Now, um, since the three sides there here has no label yet, what I'm going to do is to label them arbitrary x sub I. So we have a x sub 1, x sub 2, x sub 3, and then just assume an arrow there, a direction. So for this one, since this is, um, we can have this as an alternative. So for example, this is going in here at point A. Look at here, 30. It goes in here at A. So we expect that x2 will go out here, and then x1 will go out, flow out. Okay. Now for um, C here, x3 is here, so we expect it will go there at the B, and then that's it. So we have this one. So it says there, class, that the direction of the x1, x2, x3 are not necessarily to need. We need not be concerned with the direction, because if some of the directions are incorrect, since an incorrect direction will be signaled by a negative value. So for example, if this is x2, and if we solve a negative value for x2, then change the direction. The direction must go there at point A. Okay? So this directions are just initial, so it's not the final one. Okay? And then we create a table. For example, point A, flow in is 30, flow out is x sub 2 plus x sub 1. And we have this. For node A, flow in is 30, flow out x sub 1 plus x sub 2. X1, x2, sorry. Next, we have B. For B there, flow in are the x2 and x3. Then flow out is this 35. So we have that one. And then the C is this, and then the D is this, if you go back to the figure. Now what to do here, we arrange them. The variables are this side, and then the numbers are in the other side. So we have this values. Now it's easy to do the x3 and x1 because there are just numbers here. So 55, transfer the 15 there, minus 15, your x1 is 40. Here, 15, transfer on the other side, so we have there 60 minus 15, your x3 is 45. Now you substitute it here, your x1 is 40 in the first equation. So 40, this is x2 is equal to 30. Transfer the 40 to the other side, it's 30 minus 40. So your x2 is negative 10. So class, we solved now an x1, x2, and x3, and we're done. But your x2 there is negative 10, so the correct direction now for your x2 is it will go to A there. Okay? Change the arrow there. It will go to A, not here, going to the B node. Okay? And that's it. Next, another example is about traffic patterns. So the following network is shows a proposed plan for the traffic flow. We have this one. So here is 200. For example, class, this is an average number of vehicles. 200 will go here, 500 here, exit, 700, 600 here, 400, 400. And that's it. Now the question, going here in the traffic light, there is no value. So we can let that as an X there. And these are the following questions. How many vehicles per hour should the traffic light let through to ensure that the average number of vehicles per hour flowing into the complex is the same as the average number of vehicles flowing out? So this question is actually asking for the number here going to the traffic light. So let x be that value, and the flowing in we compute all the flowing in and all the flowing out, and that's it. We have this one. Okay, if you can see it here um in the figure, this is flow in 500, flow in 200, flow in 400, and flow in 600. So add all of them, and then you add the flowing out. The out there is 700, 400, and then the x there. That is why you have this. And then we can solve the x now. um This is x plus 1,100, and then the total here at the other side is 1,700. Transfer the 1,100 to the other side, it becomes 1,700 minus 1,100. So your x there should be 600. So we have now an x is equal to 600. Next question, we have this. Assuming that the traffic light has been set to balance, so it's now balanced already. If your x there is 600. Question, what is the average number of vehicles per hour that will flow along the streets that border the complex? So it's here, class. They're asking for this one. The x1, x2, x3, and x4 here. So what are their values? So the flow in must equal to the flow out at each intersection. So we label them. The points there are the intersections C, B, A, and D. And this one we just assume that are the following um, direction, which is correct, right? Because if this is flow in here, then it will go in here in the x2. And here 500 flow in also for your x3 here, going to be, then look at the direction because they are the same. So 600 is here, so your x2 direction is going there, then going to the traffic light. Then here also, okay. So that's it. So the directions are now the same. Then we solve them. So before we solve them, you have to create the table again. So flow in at point A, look at point A. Flow in is 400 and 600. Flow out there is the x1 and x2. So B at point B there, flow in is the x2 and x3. As you can see, the arrow are going to point B. And then flow out, so going out of the B is 400 and then the x. So class your x there, you make it 600, okay? And it's here. Because the total flow in and out of the complex are equal, your x should be 600 there. And then this will happen. Okay, here. This is 600, right? So 400 plus 600, it becomes 1,000 in your second answer. So it's here. Second row is 1,000. And we have this arrangement now. If you arrange the variables are in the left side and the numbers are in the right side, you have this. Now, if you perform the augmented matrix here, and then after that, your x1 will be in the first column. So it should be 1, 0, 0, 1 there because there is no x1 here in the second and third column. Okay, so you make x1 for the first column, x2 values in the second, x3 third, x4 with the numbers in the x4 is in the fourth column. So in the fourth column, it should be 0, 0, 1, 1. Okay, because there is no x4 here in your first two equations there. And then the numbers are there at the side. Now what to do there, you apply the RREF in your MATLAB, and you can see that all zeros will be there in the row 4. Now, if all rows there be zeros, what will happen? You have to do it like this. Your x4 must be equal to a t value there, right? It means that we have infinitely many solutions. Then after that, you substitute in our x3 the value of your x4, which is this. If this is t here, transfer it there, 700 minus t. Now the 700 minus t x3, you substitute the x3 here. So 1000 minus 700 minus t, there it becomes 300 plus t. And then this is now your value of your x2, 300 plus t. You substitute it here in your first equation. So 1000 minus 300 plus t there. It becomes 700 minus t. And that's it. We have the average flow rates now, which are the following. Okay. Now, for your t values, um, since your t is the x4, okay, look at your x4 here, class. Your x4 is here. And then we have there 500 and 200 going in, flowing in. So for flow out class, the maximum number for x2 that will go here is 700. That is why your t is between 0 and 700. Okay? Now for your x1, just substitute the t there. Your t, when t is 0, it's 700. When t is 700, it's 0. So your boundary for your x1 is 0 to 700. And so on. You apply the x2, x3, and x4. Okay, I can explain the x2 there. Now your x2, look at your x2. It's 300 plus t. So your t is from 0 to 700. Just substitute 0 there. So if your t there is 0, so 300 plus 0, it's 300. That's the minimum. And then the maximum number of t is 700. You add the 700 here. So 300 plus 700, it's 1000. So the maximum value of x2 is 1000. And that's it. x3 is from 0 to 700, and your x4 is also 0 to 700. Next, we have a battery is a source of electric energy. By the way, you have something like this in the test. So you have to, yeah, I don't know. I didn't see yet the test, but the previous test, they have this. Um, it's about measuring the voltage and then the current and then the resistance. So this is the formula. E is equal to IR, and you are given there a circuit later. Okay, we have there a source of electrical energy, that is a battery, and a resistor is an element that dissipates electric energy. So you have this definition 2.2. Um, we have also node here. It's a point at which three or more wires in a network are joined. And we also have a branch, a wire connecting two nodes, and a closed loop is a succession of connected branches that begin and end at the same node. So if you have this one in 2.1, this electrical network has two nodes, this point here and this point here. That's a node. Now, three closed loops. We have this first loop, second loop, and the third loop. All of that, the big one. Next, two inner loops you have there, and then one outer loop. We have the one outer loop. Okay, next, theorem 2.2. The sum of the currents flowing into any node is equal to the sum of the currents flowing out. Okay, you have this characteristic also. This is the Kirchhoff's current law. And the voltage law is this one. The sum of the products IR, the current and the resistance around a closed loop is equal to the total voltage in the loop. Okay, again, the sum of the products of all your IR there around the closed loop is equal to the total voltage in the loop. Okay, if you have this one, determine the currents I1, I2, I3 in the following circuit. Okay, as you can see, we can have these directions. Now for your A there, flowing in is I1 and I2. Flowing out is I3, correct? So we can have this table. I1 plus I2 equals I3. Now for node B there, for node B, going in is your R3 there in that direction. And then this is the going out there, the I1 and the I2 are going out, correct? Look at the lines there. Okay, so that's it. I3 is equal to I1 plus I2. And they're just the same, right? These two equations are just the same. Um, this is actually um, symmetric property of equality. Okay. Next we have we go here. What can we form here? Look at the current I1 class. This is the current, and then the resistance here is 5 amperes. So 5 times current 1, I1, and then here you have your 20 is the resistance here, 20 ohms, times the current here is I3. It says there that the sum of the product of your current and the resistance is equal to the total voltage. The voltage here in this loop is 50 volts. So you have your I1 times 5 plus 20 times I3 is equal to 50 volts. Let's see if we are correct. So it's here. I have 5 times I1 plus 20 times I3 is equal to 50. So we have there applying the Kirchhoff's voltage law to the loops produces this one. Now going there to the other loop here on the right side of the loop. Um, this is the direction class going there. And then look at your, when you go here in this loop, the direction of this one class is the same with the direction of the loop. That is the current. Look at the current. Okay, so we use positive values there. Now here, if you can see, the direction here is different from the direction of your current. Okay, look at this one. It goes here. This is clockwise, correct? And then your direction of the current here is counterclockwise direction. So they have opposite direction. So what to do? Make them negative. So we have here negative 10 times I2 and then 20 times I3 is equal to 30 volts. So you have here negative 20 I3 minus 10 I2 is equal to 30 volts. And you can form this three equations now. You have this two. And where we get this, the I1 plus I2 minus I3 is equal to 0. We got this from here. Just subtract I3 here in the other side, and the other side becomes now 0. So that's I1 minus I3 is equal to 0. That's from that table. Okay. Now, if you solve this, the results are the following. I1 is 6, the current I2 is negative 5, and your I3 is equal to 1. And we're done. Next, we have chemical compounds are represented by chemical formulas that describe the atomic makeup of their molecules. So example 3.1 for water, it's H2O, chemical formula. For stable oxygen, that is O2. For methane, we have CH4, then stable oxygen O2 reacts to form the CO2, and water H2O is there. Okay, so we have this chemical equation, CH4 plus 02 map to CO2 H2O. By the way, class, do you have this in your chemistry to how to balance this? Okay. By the way, when I was in high school, I just substitute numbers there and I can balance it directly. I didn't know that we can use system of linear equations in solving this kind of problem. I just knew it because of this slide. Okay, so a chemical equation is said to be balanced if for each type of atom in the reaction, the same number of atoms appears on each side of the arrow. So if you count them, C here is only one. H has four. Here the oxygen has two. Here your C has one, so the same C. But the oxygen here are not the same. Here we have two and then one here, so three in the side, and then this one has two. For the hydrogen H, we have here two, and then here is four. So this is not balanced. So what we're going to do, we multiply numbers here at their sides, okay, to make them balance so that they have the same number of atoms. Okay, so we can multiply them x1, x2, x3, and x4 there. And we can find this equations. Um, for C, this is x1 plus, okay? So to make it the same with this, since your C here has only one also, it should be equal to x3. So your x1 must be equal to x3 here. Next, hydrogen. For your hydrogen class, it's 4 here. So 4 times x1. And here for the hydrogen, we have 2. So 2 times x4. So 4x1 is equal to 2x4. Next oxygen value here, we have 2. So 2x2. And here we have 2 in the x3. So 2x3. And 1 oxygen in the x4. So plus x4. And we have that values. What to do? Transfer the variables there to the left side and we can form this. Then equate them all to zeros because you transfer them right in the left side. So this is a homogeneous linear system. Now what to do? Perform now the uh, transform them into augmented matrix, but do not include the 0, 0 there. So just this matrix, the numbers here. Then after that, perform the RREF, reduce that to row, um, reduced row echelon form. You have this form now. So as you can see there, they're all one here in that is your x1 in this column. This one is for x2, and then this column is for x3. Now what happened is there are too many numbers here for your x4, and we have no row for x4, so we have to let our x4 there becomes a free variable. So if their x4 be equal to t, so if that is t, all here, you multiply this by t because this is for your x4 column, right? Then transfer to the other side. So minus 1 half t, transfer to the other side, it becomes 1 half t. So your x3 is t over 2. Your x2 here becomes, this is negative 1 times t, transfer to the other side. In the equation, it becomes positive t there. So your x2 is t, and your x1 is t over 2, where t is arbitrary. Okay, now let t is equal to 2. So the equation can be balanced by letting x1. Okay, if your t there is 2, so 2 over 2 is 1 for your x1. Your x2 is 2. Your x3 is 2 over 2, it's 1. And then your x4 now is 2 because we let t there be equal to 2. And we have this x1, x2, x3, x4. And we substitute it here in our equation. We have the x1, x2, x3, x4. You change them now. And we have this. And you will be shocked like, oh, why they're different? Yes, it says their x1 is 1, x2 is 2, x3 is 1, and x4 is 2. Now, if you substitute that values class, it is correct. And this one also is correct. But here in this one, your t there is 4. Okay, when your t here is 4, your x1 is 2, your x2 is 4, your x3 is 2, and your x4 is 4. Okay, by the way, for this one we use the t there is equal to 4, not this t is equal to 2. Okay, again, this answer is correct. These answers also are correct if you substitute it there. Okay, and that's it. So thank you for your attention. And the time is 10:48 already. So next meeting, we will continue discussing the vectors and the basis, and then after that, maybe we will finish like for the 1 hour session, and then after that, we will have a midterm review for 1 hour also. By the way, if we cannot finish the midterm review, I will just make a complete slide of it with questions and then answers for you to study. Okay. Or maybe we can have special session next week. Um, because next week I will not meet you. I will just give you some materials there. But if it's not enough for you, if you want to request me something like, can we meet you for next week? Yeah, it's okay with me. Okay? And that's it. Thank you everyone for coming. Goodbye. Thank you, Dr. Yu. Okay. Bye everyone. Have a nice day.